Hello everyone, my name is Sinziana Paduroiu, and I would like to first thank the organizers for arranging for me to give this talk. And I'm also very privileged to have it on a Thursday after gathering information from the distinguished speakers before me. Now, this is yet another dark matter talk, but in my defense, I will speak about a certain dark matter aspect that has not been addressed in the previous lectures. And I will try to also put together some pieces in a puzzle that's structure formation and structure evolution in the universe. So we've been talking in the second day, I believe, about the theory of everything. And if you like to build such a theory and bridge together different aspects from quantum mechanics to large-scale structure to particle physics to thermodynamics and so on, you will need to explain this picture. By explaining this picture is either come up with a solution and a particle for the dark matter, or show that this picture, against many pieces of evidence found in the astronomical observations, is in fact wrong. Now, I won't be able to speak about all these things, but you can ask questions about everything from the large-scale structure in the universe to the small-scale structure. I will briefly speak about several candidates in the dark matter particle community. I will try to address what's the connection in between dark matter and the information and complexity in the universe. And I will give some clues on where we can still look to find hints on what dark matter is and what it does. Now, this is the picture that people refer to when they talk about large-scale structure in the universe and the filaments and so on. And as you can see here from different perspectives, you kind of get the same structure. Some of these are surveys coming from observation of galaxies. Some of them are from the simulations. The interesting thing is that even if you simulate different particle candidates, some of them will still produce this large-scale structure picture, even though many of the people in the community would say that cold dark matter is the one that explains best the large-scale structure. Now, in terms of candidates for dark matter, we have basically ruled out anything coming from baryonic matter, and by baryonic it was a question in the first day, I think. We also include things that we like electrons. So everything that we do see in the universe is included in the baryonic physics, all the visible matter, let's say. And then the non-baryonic candidates are a myriad of hypothesized particles. And if you look at the papers on dark matter, which are now 500,000 papers published, 98% of those papers are actually talking about non-baryonic candidates, just a little piece of trivia. Then we have the other theories, the alternative theories, as they are called, which can be from the modified Newtonian dynamics to anti-gravity virtual particles, the scalar tensor vector gravity. We have the emergent gravity that Eric Verlinde was speaking about the other day. And we have other theories that are saying that we live in a computer simulation. And it was an earlier talk by Edward, who was speaking about the cellular automaton. Now, if we do live in a computer simulation, I would rather prefer to have a more code-theoretic approach, in the sense that still have syntactical freedom when it comes to the universe, rather than a deterministic one. So you can still have a code-theoretic universe without having a complete cellular automaton. And then there's another question that arises if you think about these theories, which is, what drives the universe then? What's the purpose if you have such a code-theoretic universe? And is it actually the higher complexity of the higher rank of organization? So is such a thing that a universe, as many systems that we've seen in biology and so on, are actually driven by their all evolution towards a higher level of complexity and organization? Now, since I was speaking about the non-baryonic candidates, these are just few of them. and depending on the mass and their energies, that can be put in between cold, warm, and hot matter. Most of the papers, however, and the detectors, and you've seen it earlier in the movies, are concentrated about on the first two candidates, like axions and then neutralinos. And usually when you see that there's a new observation that shows that the dark matter has problems, people usually refer to simulations or detection limits coming from these two models, axions and neutralinos. Now today I would like to focus on a third model, which is sterile neutrinos, or something like sterile neutrinos, which decouples while still relativistic. And while I won't try to sell you this model as the best alternative when it comes to dark matter, because I'm still agnostic myself, it's just that I'm agnostic in between fewer options, I would show you that this is giving a lot of explanations to what we see in the universe and what other models are having difficulties with. Now, this has been going on for a while in the community, this battle in between cold dark matter and warm dark matter people. And it's been because lambda CDM alone, without the baryonic component, is not explaining the number of satellites that we do observe in the universe and the cores that we do see in the galaxies. Now, this was partially solved in the community because many baryonic processes, when you put them by hand in your simulation, are going to produce cores and are going to lower the number of satellites. However, there are still other problems and observations in astronomical observations that show things that cold dark matter doesn't predict. For example, there's a large number of pure disk galaxies which have not been reproduced in cold dark matter simulations. To my knowledge, there's only one simulation that produced with very fine tuning parameters core in dwarf galaxies, and nothing in the Milky Way type of galaxies, and we know that there are many of them that are pure disk galaxies. Then we have galaxies that have never suffered mergers, which is again a problem in the cold dark matter simulations, because when you form the structures hierarchically from the beginning, you can't really avoid mergers by redshift 0. Then we know that the dwarf population in voids is much more in agreement, and there are several papers on this, with the warm dark matter scenario. And by warm dark matter, as you've seen before, I would actually refer to the kilo-electron volt, which is the prominent candidate, nothing hotter than kilo-electron volt, because if it's something hotter than kilo-electron volt, it won't form the structure indeed as we see it in the universe. And then you have these dark galaxies that are showing up more and more, and of course they're very hard to observe, but this doesn't mean that there's not a lot of them in the universe. Like Dragonfly 44, that's a large galaxy that has I think a factor of 100 fewer stars than we see in the Milky Way. So it's a galaxy that's predominantly dark, even though it's large, it's not like a dwarf galaxy. And of course, the last thing is the fact that if you look at all the limits coming from the detection experiments, you'd see that basically everything is ruled out. There's only one narrow band in which they can still detect cold dark matter. So after years and years, this particle has still hasn't been detected. Moving towards warm dark matter now. In theory, also here you can hypothesize different particles like sterile neutrinos and gravitons, and then particles that are thermalized, rethermalized. So it's not an easy way to constrain the particle even in warm dark matter. But what these things have in common is they have a free streaming lens, which in turn gives a cutoff in your power spectrum and a velocity dispersion. What this does is first prevents structure to form below a certain scale. This is very strongly depending on the mass, so this depends on the mass of your particle, if it's kilo-electron volt 1, 2, 3, or something lighter than that. And so this prevents structure from forming below a certain scale, which in some regions completely changes the structure formation mechanism. In some just delays it, and it's a much more complicated structure formation. That's at the structure formation level. Inside the galaxies, there's another thing that happens, because when you have free streaming lens and for fermionic particles like the ones theorized, what you do is you have a maximum phase space density, and this translates in a certain limits constant core that you would have in your galaxies. On top of this, these are fermions which are having quantum pressure, which we've seen in the literature in the past few years that it has a very important effect at the cores of the galaxies. The downside is that all these things that I talked about are very hard to simulate. So what people do in simulations, including me, is we just cut off the power spectrum of the particle, and then some of us also add the velocity dispersion to those particles. So you see that it's a very rough approximation of what the warm dark matter particle can actually do. So yes, I would like to make this distinction because it was raised in a conversation. When I'm talking about massive neutrinos, and when people talk about massive neutrinos, like the right-handed neutrino, the sterile neutrino, when we're in cosmology, we refer to something that's in the kilo-electron-volt range. That cannot be, it was proven that that cannot be the right-hand neutrino for the triplet that we already observe. So for the light neutrino. So you need a different triplet that will give you that massive neutrino. In the particle physics and in the people who are working, in between the people who are working in detection, when they talk about massive right-handed neutrino, they refer to the right-handed neutrino to the triplet that we know of, which is in 1 electron volt, and has been this recent result by the mini-boon experiment, where some inconsistencies in between what they expected from the data and their actually detection, they explained by 1 electron volt right-handed neutrino. So it looks like we already have 1 right-handed neutrino in the universe. And I really like this quote from Matthew Buckley, because this doesn't help with anything, but this is not the reason for the universe not to produce particles. So just to give you an idea, this is a difference in between a cold dark matter simulation at redshift 0 and redshift 3, something in the kilo-electron volt range, redshift 0 and redshift 3, and something that's hotter than 1 kilo-electron volt dark matter. You can see already the difference in the number of satellites that you form. This is with 200 eV, and this is 50 eV. You see that with 50 eV, we know that this is completely ruled out because you don't form any structure by redshift 0, and this is just a zoom in of the same picture. Now, indulge me when it comes to the equation. I just want to show you that when we do the simulations, this is how we cut the power spectrum depending on the mass of the particles, and we use, most of the people who are doing simulations use this formula, which gives a dependence on the velocity dispersion of the particle to the mass of the particle. But this is very strongly dependent on your model of particle production, which doesn't make things easier at all. So if you just look at where this formula comes from, it comes from the number conservation of the abundance of neutrinos with respect to photons, and it gives in the end, with like the critical density of the universe, it gives in the end a very high number of, for 1 kilo-electron volt, of degrees of freedom at decoupling. I would like to remind the people in physics here that for the standard model you have 107 degrees of freedom. For the supersymmetric extension of the standard model you have 229. So people usually, for stellar neutrinos, were using something in between just to be on the safe side. This actually shows that within this model you need a much larger number of degrees of freedom at decoupling. Now, if this is true, this is again one model. If this is true, there has been work that was looking at the, and it has the assumptions of entropy production and negligible chemical potential. So in order to explain from the particle physics point of view how you get so many degrees of freedom at decoupling, this is work in progress done by Garrett Lisi and Mike Rios, and I'm just going to throw it out there. I mean, we can discuss more about this, but I'm not going to get into the details of how E8, which is a structure of rank 8, 248 dimensions. I mean, people in string theories have been looking like this for a while. Now they're looking at Lie algebra structures in the higher dimensions, that in projection to a 4D and 3D would give this high numbers of degrees of freedom in terms of how you would produce these particles. So there has been work in particle physics at this level. Now, if you just change your assumption just by a little bit, we were looking at number conservation, non-entropy production, quantum pressure, and then having this exchange potential. And independent of the cosmology, basically, we got a completely different correspondence in between the velocity and the mass. It's also a different power law, not just the factor in front, which for a certain mass of the particle would give you a difference in between, like a factor of 10. What I'm saying by this is that for the same velocity dispersion, when you're tracing back to your mass, you would have a factor of 10. So with the same velocity dispersion, depending on your model, you can have 1 keV or 10, which is a very large difference. And in simulations, it's actually cumulative when you look at the high redshift. So this basically shows that in order to constrain the mass of the particles from the observations, which are going to give you the velocity dispersion, not the mass of the particle, to a mass that you're going to plug into a detector, it's a very hard thing to do in the absence of a universal model of particle production for warm dark matter. And this is exactly as I was saying, in between different models of dark matter candidates, the difference between mass and velocity. So when you hear people that are doing like Lyman alpha forest fits, which are comparing the simulations with the data from the observation, that you have a strong limit of 2.3 kilo electron volt and so on, please do not trust them, or at least take them with a grain of salt, because those are very model dependent. I'm just gonna, since I have only 5 minutes, I'm just gonna go to the movies of structure formation just to show you what I mean by the difference in the structure formation. So this is a vintage movie by now. It's a movie I will start with, called Dark Matter, just to remind you how the structure forms in cold dark matter. It's been done in 2003 by Jörg Diemand, and the rest will be warm dark matter movies. So you see that everything clumps and merges together. This will end up in a galaxy by redshift 0, and this is something that shows how structure forms in cold dark matter. When you're looking at warm dark matter, instead of looking at few kilo electron volts, which require a very high resolution, because these effects that I was referring to earlier are going to be quickly swiped off by the other stage in the evolution, we were looking at 200 eV, which is a transient regime in between. Yes, it's a transient regime in between something that's hot and is purely top-down in structure formation, and something that's predominantly hierarchical, like in cold dark matter. So you see that you have these large filaments that are collapsing top-down at the intersection of the filaments, and in some region these galaxies will remain isolated, will not have any mergers by redshift 0 in the voids. Some will merge together and form large clusters, even though they, like 4 of them were really big, formed at the beginning. Some of them will be purely accreting matter. So when they form at the intersection of the filaments, are just going to start accreting more and more matter and grow bigger by accretion. This is just a difference in between, but it's not the best resolution for the screen to see this difference. Trust me, there is a difference in between the one without the velocity dispersion and the velocity dispersion when you add those two together. And this trend on whether you have more top-down in one side or more hierarchical in the other depends only on the morphology of that region. And we found out another correlation, like here, for example, you have a very you have 4 large halos that are forming and then they're going to merge together. This is going to become a cluster very quickly. Here you have isolated galaxies. The preservation of filaments is gonna be for like a longer time, and the way depending again on the mass and velocity of the particle, the way in which particle travel from one side to the other is going to be more important, in the sense that you have a larger region from which you bring information into your halo at redshift 0. This is something that poses still a problem for simulators, because if you want to have a halo that you resample with higher resolution particles, you would need to sample a larger region, and sometimes those are not connected in the initial conditions, which means that the information that you're going to get at redshift 0 from a larger area of the universe. This is a purely top-down halo formed at the intersection of the filaments. You can see here also, this is a zoom-in of the same halo. You can see here the collapse, and you see these shells and caustics that have been observed in the universe. In some cold dark matter simulation you see them as well, but in warm dark matter there's a feature that happens. You can see it in any halo whatsoever. And this is again like halos that are going to merge together, and this one is going to show another problem that's called the artificial fragmentation along a halo. But that's a thing that I'm not gonna address for now. And this is a simulation that I was referring earlier when I was asking Pratika about this. This is the highest resolution warm dark matter simulation ever done. The mass resolution per particle is 300 solar masses. That's about 2-3 orders of magnitude higher than the normal simulations. And they used gas as well, and this is done for a proper particle, like 3 kilo-electron-volt. And they show that unlike in cold dark matter, where you're always going to form the galaxy first and then stars at the center of the galaxy where the baryons are attracted, in this scenario you actually form molecular hydrogen and stars in the center of the filament, in different regions in the center of the filament, which in turn prevents the filament from breaking so soon. So you basically start to form galaxies and presumably supermassive black holes at the center of the inside the filaments instead of in the center of the galaxy. So just trying to get to yeah, sorry, this is not working. Yeah, I can't because it doesn't work in the previous one. It's back. Okay. Yeah, sorry about that. So these are the different structure formation scenarios that I was telling you about. You can find them in all the simulations. These are the caustics and shells in warm dark matter with respect to cold dark matter. This is a difference also that we see in the velocity magnitudes in those halos. And I'm just going to quickly skip this. This shows that basically it's not enough just to have the velocity dispersion and the power spectrum to form cores in the galaxies, but it has been shown that if you add the fermionic pressure, you can have the cores in dwarf galaxies that we do observe. So that's without any baryonic processes. And this is what we get in the end from all this is basically we have a different structure formation mechanism at all scales, which is going to be more visible in lighter particles simulations and less visible in the few kilo-electron volts, but it's always there. You have softer cores. You can form bigger disks in warm dark matter. You have fewer satellites. The quantum effects we know that are important, and you have these non-local aspects due to the free streaming of the particle. There's a possible explanation for the early massive black holes formation if you do form stars before you form the galaxies in some scenarios in the early universe. And all your structures are going to have a higher degree of complexity. Now, again, as I was saying, do not trust simulations and prediction from the simulations, but some of these things, after doing many simulations with many different particles and different resolutions and so on, I can say that the mechanism of structure formation in warm dark matter is basically a hybrid mechanism with two limits, like one being cold dark matter, which is predominantly hierarchical, and the other one being hot dark matter, which is predominantly top-down. And we know that the maximum phase space density and the quantum effects are important when we are talking about the cores of the galaxies. And of course, those help also with the velocity dispersion of dwarfs and other observed structures. And we know that neutrinos, as like a lighter mass triplet, already exist. Of course, this is not an argument, but this just feels good for people who are trying to detect even heavier neutrinos. Now, what it hints to is, in the end, kilo-electron volt mass particle. By kilo-electron volt, it's a range, depending on your mechanism of production. A heavier neutrino triplet, in order to have this sterile neutrino on the right side that's much massive, and higher number of degrees of freedom at decoupling within one of the models that I was telling you about. So what we need to prove this is very easy. We just need this mechanism of particle physics that produces a higher number of degrees of freedom with the right mass. Then we need to actually produce the particle with the right mass. Then we need a big simulation with the right mass. Then we need $1 billion to build, this is a supercomputer, to build a detector for such a particle, and a lot of luck. So in terms of how dark matter works, if I'm to bet, because Professor Padmanabhan was placing this bet with cosmological constant. Now, I would actually bet if it's still a particle on this one. So if anyone is trying to honor that bet, please feel free if you still believe in cold dark matter. So thank you very much.
Okay, thank you very much for that talk. Questions?
All right, okay. Who's got the block box? Go down to front there.
Does it? Yeah. Okay, so you showed this warm dark matter simulation. You pointed slightly at the beading effect in the filaments. There's a code called cold ice. Have you worked with that?
No.
But you know of it?
You're referring to the fragmentation problem.
Yeah.
Yeah, so that has been already like solved in the community by different things, sampling in phase space, or using more glass-like, even though you still have filament in the glass-like codes. So it's been getting rid of, sort of. But what I wanted to, I briefly went over because I didn't have the time. I showed that picture because we know in that case it's scaling with the resolution. So you can just increase your softening in the simulation if you're not interested in that scale and get rid of the halos. The problem is if you do form stars, as in the other scenario with a lot of gas, if you do form stars inside the filament, that fragmentation is actually going to be real. And it will look pretty much like the artificial one, which in turn, when you look at the, as Pratika was saying this morning, when you look at the mass function from the simulation, and you say, we didn't form galaxies so small, what basically you mean is the that scale that I was talking about, which is connected to the fragmentation scale. Those galaxies are going to be there. So you just get rid of them from your sample because you say they are artificial. But if you form them the other way around, then those are actually going to be pretty much real. So you should include them in your sample. So yeah, but the fragmentation problem is pretty much solved now with the new simulations. Yes.
Also, you mentioned quantum effects and increased complexity in the warm dark matter case. I would think that the just looking at, because there's more structure in a cold dark matter case, I was confused about why you said there's more complexity in the warm dark matter.
Because you have different stages of structure formation that are going to imprint different signatures in your halos. So when you form them by mergers, the difference in between your halos in cold dark matter, if you don't take baryons into account, are just going to be mass. Right? You're not going to, the profiles are going to be the same, it's just going to be mass, and the region from where the information comes from, we're just going to be scaled to that, basically. When you have warm dark matter and you have all these kind of like crazy formation scenarios, you can first have halos that just have information from when they formed. They don't have mergers. In voids, you have these kind of structures that are going to look completely different in their internal things because they don't have mergers to disrupt them. So because you form them in different scenarios, each of them is going to look different and is going to carry a different type of information from the beginning. And the first thing you said was the quantum pressure?
Yeah.
Yeah.
So is that related to some recent work about fuzzy or wave dark matter? Or?
No, that's also something that has to do with quantum pressure. But no, the fuzzy dark matter is not something that I worked on. I know that that's a new model, and I speak with the people who started it, so we've been talking about this. The quantum pressure in this case, because it's fermions, there were those papers by Destri and De Vega and Sanchez where semi-analytically they just showed that with kilo electron volt, if you have a Fermi-Dirac distribution, which is not something we use in simulations, we use Maxwell-Boltzmann. If you have a real Fermi-Dirac distribution and you look at the equations of state and you put the quantum pressure as a term in, you actually get the cores from dwarf galaxies to Milky Way galaxies. You get the observed cores just from that degeneracy, basically, at the center, without any baryonic physics for 2 kilo electron volts dark matter. In simulations, that's very hard to implement. You can put it by hand towards the end because it's not going to be important when you form structures. But that's hard to implement, and you only get the core that you get from the maximum phase space density and the velocity dispersion, and that's not enough. It's still going to be, it's always going to be cored, but the size of the core is not going to be enough as the one observed. Also, on the other hand, even without quantum pressure, which you shouldn't neglect, but if you put baryon in something that already has a core, you're just going to get a bigger core. So when you compare it with cold dark matter plus baryons, you're just going to get better results, not, yeah. Yes.
Thanks for the very nice talk. I have a question about metals, because in the filaments, you're forming, must be very massive stars, and so is there a difference then in where you might find the heavier metals in the two warm dark matter and cold dark?
Well, that's something that was sort of triggered this morning as well. These studies haven't been made. I mean, there's only one simulation that was stopped at redshift 13. So that means actually population 3 stars. What I believe is going to happen is actually you're going to form those stars that are going to trigger supermassive black hole formation early on, that are going to grow by dark matter. And whether that is going to give from the stars a signature in metal richness from so early on, I'm not sure whether that's going to be seen. I mean, if the effect is going to be important enough to see it when you look at observations and say, well, these metals, because it's just you just trigger molecular hydrogen that early on, which in turn can form stars, but in such a high density environment and with this gradient in temperature, because your filament is not going to allow you to just move around, I think it's that's going to trigger a supermassive black hole formation. And it's not going to, yeah, those stars won't survive to tell us now what's going on. But we haven't tested this.